This video looks at how predictive functional control includes integral action. The previous three videos then have introduced the core concepts of PFC for tracking constant targets. The basic idea is to choose the current input such that the output prediction n samples ahead matches a target trajectory with the desired closed-loop dynamics. However, as with all predictive control laws, some further analysis and requirements are needed to ensure, and this is the key thing we're doing here, that we're going to get offset-free tracking in the uncertain case. So just a reminder of what PFC does. What we do is we choose a target dynamic, which in essence is a first order response, which goes from the starting point to the end point following a given first order dynamic, and then what we do is we force the output prediction to match that at a single so-called coincidence point using just a single degree of freedom, which is the predicted future input. Now this target can be written down explicitly. We've done it here. You can see for n samples ahead, it's yk, that's the current output, plus r minus yk times 1 minus lambda to the n, where this lambda is basically the dynamic you've forced into this first order. The lambda is a discrete pole equivalent of the desired closed-loop settling time Ts, so you can actually show that there's a nice relationship if you want it. So if you want to do things in continuous time, you define Ts, you define your sample time for the discrete system, and then you can work out what lambda is. Offset-free tracking then. In order to ensure the PFC algorithm delivers the system to the correct steady state, you need to establish a consistency condition. And this is what that might be. If the current output equals the target for all past samples, so in other words, if the system's already at the correct steady state, I should have added the word correct there, prove that the algorithm will propose the current input to be unchanged. So in other words, what you want is, if I'm at the correct steady state, then this control law should keep me there. So this is what we're saying. We're saying if I'm already at the correct steady state, then the proposed value for the input must match the current value of the input. And you'll notice here at the end it says for all I. So all the future values of the input must match the current input. And similarly, our predictions must be such that the future output predictions match the current output, match the target. So this is what we want the control law to deliver. This is called unbiased prediction, and it was discussed at length in chapter 1 of the MPC series. So you can look at that if you want to do it slightly more slowly. Here we'll just demonstrate that the use of an independent model is sufficient to make this work. Here's our independent model. We did this in the previous video, so it's just a reminder of what's going on. The process is modelled as some unknown GP and some unknown disturbance. We have a model which we know exactly, which we call GM, which we're going to simulate in parallel with the process, and that has a model output YM. And what we do is we compare the process output and the model output, and that gives us this term here, DM. And this term basically allows us to correct for any bias due to uncertainty in GP and uncertainty in D. So that DM's given us the difference between the process output and the model output. And we're going to use that to correct any bias. So here's an example for this steady state prediction. We're going to assume that the process is at a steady state value of A. The model is at a steady state value of B, and it's key that you recognize that. We're assuming everything's at steady state, and therefore this DM term has to be A minus B. And now what we want to do is find out what happens if we assume that the input doesn't change. So we already know that yp of k equals ym of k plus dm, because that's a definition. And we know that if we keep the input the same, then the future values of ym must be b. We've got to assume that the future values of dm are the same as the current value because we've got no better information. So if we assume that the future input's not changing, then we've also going to assume that the future output is not changing. And something went wrong there. And therefore, nothing's changing. So yp of 0 equals r implies that yp of k equals r. Now we're going to look at this in slightly more detail with some specific numbers. So I'm going to take a first order model here, g equals bz inverse over 1 minus az inverse. I can write down the predictions for this explicitly. Here are the explicit relationships that I want. This is assuming, you'll notice, that the input is constant in the future. Now the predicted process output, you remember, is the same as the model output, but I add on this offset term d, which is yp minus ym. So that's the only difference between the two. And now what I'm going to do is say, okay, I've also got my desired dynamic, which is my first order response from the current output going towards the target. And you remember, what does PFC do? It says, let's make these two the same. That's what we actually want to do. So I've matched the prediction and the target n samples ahead. This is what I've got. So here's my target, and over on this side, here's my prediction. Now if I solve for the input, you might think this looks a bit messy, but it's not as bad as it looks. You'll see I've got some term times the target, some term times the model output, some terms times the process output. There's my offset term, and then over here I've got my step response n steps ahead. Now if I combine common terms, which I can do because you'll see that yp appears in two places, then you actually get a slightly simpler form, which is this one here, 1 minus lambda to the n times r minus ypk, and 1 minus a to the n times ymk, and then over this step response term. So you can reduce this control law to a relatively simple formulation. Now remember, what we're trying to do, we'll get there in a minute, is we're trying to show that this control law automatically includes integral. And you might be saying, just a minute, I can't see an integration anywhere here. It seems all fairly straightforward, but there's no integrator. But you'll see there is an integrator, it's just that it's not obvious. So here's my control law, which I've just derived, and you'll see the only difference I've done here is I've made the algebra simpler by writing g subscript n for this messy term b, 1 minus a to the n over 1 minus a. So I've got the current error, that's the r minus yp, times 1 minus lambda to the n. I've got the independent model output, times 1 minus a to the n, and I've got this step response term. So there's my control law. So you're still asking, okay, but why has this got an integrator? So let's assume that we're already at the correct steady state. So let's assume that yp of k equals r, and let's see what that does with this control law. So there's my control law. I've just repeated it from the previous slide, and now what I'm going to do is I'm going to substitute this assumption in wherever I see yp. So what you'll notice is I've now got an r here, and I've got an r here. Now if I do that, you'll see the lambda to the n r here cancels with that one, and the plus r here cancels with that one, and so they all disappear, and you end up with the control law, or the proposed value for the input, being this one here. Now this is nice because you'll also notice there's a 1 minus a to the n there and a 1 minus a to the n there, so they cancel. So what you get left with is this here, b over 1 minus a uk equals ymk. Now if you assumed you were already in steady state, then your steady state would be such that this equation was true for uk minus 1, and therefore to make it true at k, you just have to choose uk minus 1 equals uk. So in other words, the proposal is that you are not going to change the input. So what we've shown here is that this control law, this one up here, will give you offset-free tracking in the steady state, and that's a sort of indirect proof that there's an integrator. So we'll do some numerical examples to do this, and then we'll do a direct proof in a minute. So the code is in this file here if you want to go and look at it, video1_4 pfc-ex1. And you'll notice we've got a model, and we've got slightly different parameters in our process to represent model uncertainty. So if I run the simulation, here we go, lambda equals 0.75, n equals 1. What do you notice? I've got offset-free tracking. So there must be an integrator in there. It's indirect proof, but it's giving me offset-free tracking. What happens if I change the parameters? Lambda's 0.75, n equals 3. I've still got offset-free tracking. Again, I'll change the parameters. So what parameters have we got now? Lambda's 0.7, n equals 3. And again, you can see I've got offset-free tracking. So there must be an integrator in this control law. Here, I've added an input disturbance. So you'll notice we've got just a target in the first bit along here, and then we've got an output disturbance, and then we've got an input disturbance. I can add all these different difficulties, but what do you notice? I get offset-free tracking. It's working. So we've given you an indirect proof that there's integral action, but now what I'm going to do is give you a direct proof that shows you that the integral is an explicit outcome of the use of an internal model in conjunction with the given control law. Now what we're going to do is we're going to do it for the first order case. Obviously you can do the same sort of algebra for higher order cases. So here's my control law. You'll see I've written it down at the top in the compact form. I've got this 1 minus lambda to the n times r minus yp. So first of all, where does that come into my control law? Well, you'll see here's yp, put it at the end here, here's yp, here's r, I put a plus and a minus, and so you'll see that this signal here is 1 minus lambda to the n times r minus yp. So that's the block diagram representation of this first bit. I've also got a bit in here, 1 minus a to the n times ym. So you'll see that's represented here. So if this signal in here is ym, then this signal coming out here must be 1 minus a to the n ym. So if I put a plus and a plus here, then this signal represents the numerator in the block. Now, what happens next is you'll see that numerator is divided by b 1 minus a to the n over 1 minus a, which is all that's in this block, so you've got u here. And the only thing remaining is where does this ym come from? Well, ym is linked to u through the independent model, which is here, bz inverse over 1 minus a z inverse. So you'll see I've now got a block diagram equivalent of this control law. And what I'm going to look at in particular is this loop in here, this inner loop. What you can show is this inner loop actually reduces to this form here, to some k times 1 minus az inverse over 1 minus z inverse. And there's the value for k. So basically that inner loop, if you look at it, represents or includes integral action explicitly. If you just do the algebra, it comes out explicitly. So if I rewrite my control law following this algebra, here it is, and what do you notice? There's my effective control law with the internal model embedded, and here is my integrator. It's actually explicit, and so the integrator comes out as a combination of this inner loop with the independent model. So the implicit incorporation of integral is now transparent. Obviously we've done it for a first order case, and your control law, if you want, can actually be represented in this form here. And you might view that as an advantage, because now you don't need the independent model, you don't need this internal loop, you can just implement this control law explicitly. And obviously the value for k was relatively simple. You can see it's up here. It's got these two terms. So, for first order systems, you can avoid the independent model altogether and simply implement the control law using the previous slide. So we've given you the code here, and what we've done is we've implemented that control law in this file, video1_for PFC ex2, so you can compare the results with the previous file, which uses the nested loops. So you can either do the nested loops, or you can use this form here, and you will see both files give you the same responses. So the summary. We've demonstrated that an elementary PFC algorithm automatically delivers offset-free tracking, and integral action is implicit. It deals effectively with parameter uncertainty in both input and output disturbances, obviously to some limit based on sensitivity, and the integrator, in effect, enters the loop through the use of the independent model, which forms an inner loop containing a forward path integral component, and we've demonstrated this explicitly for the first order case. So the key point is, even though you didn't realize you'd put an integral in there, in effect you have.